Hi, everyone. Welcome to this series of training webinars with Convergent. So today, the topic of the discussion is how to reduce exotherms with Raven, one of the softwares that we provide. So we'll start off with a short introduction, speak a bit about the presenters, a little bit about Convergent, what we do in terms of our software capabilities as well as the hardware that we provide. And then we're going to go into the technical portion of the presentation today, where we have a case study on how to assess process updates using Raven. Afterwards, we'll have a short Q&A, so if you have any questions, please type them into the chat window to the host, and then we'll go through the questions and answer them in order. So I guess a little bit about the presenters. I'm Nick Cicchini. I'm an analysis engineer in the analysis applications group with Convergent. And then Alistair McKee will be going through the technical portion of the presentation, and he's the engineering lead for the analysis applications group. So a little bit about Convergent here. As I said, we offer a suite of process simulation softwares. So today, as I said, we're going over Raven. We also have Compro, which is a plugin into FE solvers, and LIMS, which is for 3D mold filling simulation. We also have material characterization software called Kermode, which helps with model fitting, as well as we provide material characterization services. Additionally, we have and sell hardware for gas flow and vacuum leak detection, so that's called Coho. And lastly, we provide engineering services, so things like training and webinars like we're doing now, process analysis and design, and then also program and engineering support. In terms of partners and customers, we have a wide array of different academic and research partners that we're continually working with, as well as software partners that we team up with to provide our software specifically to Dassault, ANSYS, and Siemens. And then we also have a large number of industrial customers and partners that we work with on large projects. So I'll pass it on to Alistair now, and he's going to go through the technical portion of the presentation. So again, if you have any questions, please type them into the chat window, and we'll go through them in the Q&A portion.
Great, thanks, Nick. So I'll present the rest of this, and then there will be a portion for questions at the end. But please feel free to ask them as you go, and we'll address them there. I did note a mistake on one of the initial slides, and so we are definitely going to be talking about reducing exotherms today. If you have been following some of these webinar series, you'll see this is a bit of a familiar format, and this is actually by request a redo of our very first one, but just a slight update to the content as well. So when we talk about an exotherm, I thought it's important to give a bit of background for everybody. And so thermoset resins typically have an exothermic reaction when they cure. Often people study this using a DSC, that's a differential scanning calorimeter, and this is something we do all the time as we create material property models. It's one of our workhorse here for the testing. And you would get a heat flow signal, would look something like this, and that goes into the characterization process. But in a typical thermoset resin, you will have this exotherm, and this does cause lots of issues in processing. And so controlling the temperature is really crucial to get the desired properties in your laminate. Excess temperature can cause degradation, or in worst case, a fire. It can also cause variations in dimensional distortion. So this will be spring back, but uneven spring back. And there's lots of other important factors like controlling flow or distortion or porosity that all come into play. Today we're going to really focus on thermal concerns. So if you go look at a process challenge then, so if you're actually making a part with one of these resin systems, you'll have various challenges that come up. One of the big ones we see right away is the lag, and this is difference between the air temperature driving a process and the actual part temperature that the part that it experiences. These exotherms that we're going to focus on today, where it actually it's generated inside the part, but also the part and tool interaction and the thicknesses can cause these variations. And really, and I'm going to talk a little bit more about what are the requirements, but all of the parts, or all of the areas in the part do need to meet these. And so what do we look at doing, changing about a process to try to adjust these? And so there are various things that we can try. Today we're going to be focused on the two in red here, which is changing heating rates or adding isothermal hold, so changing the cure cycle, but potentially also changing the tooling material. And then sometimes you're able to actually reduce the part thickness or change it, change the part material to something less exothermic, but that's not always the case. And so if you end up with a robust cycle, you can, what we really want is to be able to control the heating rates, temperatures, minimize that spatial variation, and we're really trying to protect from this overheating that might occur. And so this really comes down to a thermal management problem. And so the process to actually cure out a part often looks something like this, where we'll ramp, an isothermal ramp. We'll have this exothermic event. This is really what we're going to focus on mitigating today. And this is followed by a hold. And when you look at those in this process, what is actually happening is we're driving heat in through the top. We have a tool here, a part representation, and we're driving that heat into it. And once that exotherm reaction kicks off, we actually have heat generated within the part. And that needs to come out to the surface. Otherwise, we have a large spike like this. And so a little bit more background, and if you've been following the webinar series, you would have seen some of this type of idea. And this is really a process requirement or process specification. And these have all kinds of looks and feels, have many different types of things specified in them. Often heating rates, min and max, max temperatures, minimum temperatures, pressure, vacuum cycles, these can all be specified within this requirements, and these can get very, very detailed. But you also might have some additional limitations for specific parts where you might actually need to have resin flow or limit the pressure due to core crush, and usually you're driven by another requirement, which would be minimizing the cost, but that's usually the cycle time, or trying to cure multiple parts at the same time. And so these often get specified out, and so we're going to focus a little on the thermal ones in this in today's presentation, but you can incorporate many different requirements using Raven. And just to make sure everyone is on the same page, I wanted to make sure we know what a cure cycle is, and this is really the prescribed air temperature that we would have. In this case here, I'm just showing a two-hold cycle, it would be called, and this is based on usually the manufacturer's recommended cure cycle. And they often have an upper and lower bound on heating rates per temperatures, and this really gives you a prescribed bound that typically your part needs to be within throughout the cycle. And this slide is familiar if you've seen some of our previous webinars, in that these are some real parts and different types of part families that you could analyze using what I'm going to introduce now as the zoning approach. And these are real parts here with a sandwich core in the middle here. This is a stringer type structure with different thicknesses here and these upright stringers. And then we have a laminate here with just different ply drops and different thicknesses throughout. And what we're going to focus on here is the skin example. Last time around, in the last webinar, we actually had done an example using the sandwich panels. And so those videos are available if you request them. So how do you break down a real part that has many different thicknesses and ply drops and do an analysis in Raven? And so we have what's called a 1D drill-through analysis. And this is essentially taking the thickness profile at any one of these sections and making the representative of that stack up here within Raven. And each zone can then be assessed for the effects of different processing conditions. So in this case here, what are the assumptions that we're making? Well, there's no, one of them is that it's a 1D heat flow, so there's no heat transfer in or out of the sides. And this is actually pretty typically true for composites unless you're right near the edge. And then the other thing that we have to make, the other assumption we have to make is that we have a uniform heat transfer coefficient at the top and bottom throughout the cycle. So in reality, that may change if you change your pressure, or there's some other factors that could come into play there. But you are able to prescribe a different heat transfer coefficient on the top and bottom. They just are a constant value throughout. And so I'm going to actually pop into Raven here and set one of these examples up. But what I'm going to introduce just at first with the big screen here is what I've done is come up with this example part here, and we have these different zones, zone 1, 2, 3, 4, and you can see here that these have different thicknesses. And so what we're going to do is represent those given a different thickness here in this 1D stack up. And we're using a composite tool here to start, and you can see the different thicknesses. Now these are just nice round numbers. These are millimeters, but of course you can put in much more complicated setups as well. And then we're going to actually assess the change in tool material and cure cycle. I'm going to pop this over here and bring up Raven, and hopefully we can see this. So this is Raven here. I'm using 3.11.9, which is just one of the most recent versions. And when you come into the software, you'll see kind of a main plot window. We have a data structure or data tree over here, a little reporting window, and a few other things. And you'll typically see this here as set up. These are the tasks, and these are sort of like a wizard that will walk you through. And so you can do these, we call them 0D runs. That's just essentially a point source. And what we're actually going to use today is the 1D tab. So this is going to be a thermal profile study. So if I bring this up here, we can see that we get the window here. And what I need to define is a few different things in this stack up. And so I'm going to actually do this here so you can see in real time how quick and easy this is. So we're going to put a heat transfer coefficient on top. We're going to put the material, and I'm going to define this as the breather material here. So I'm going to bring that down here, and we're going to define this as a 1 millimeter thick. And it's non-curing, so initial degree of cure is 1 in this case. We'll put another material in here, and we're going to use Torre 2510. This is actually a carbon epoxy material just in this example here. And for zone 1, we had 2 millimeters here as the thickness. So it's quite thin right out here on the edge. And we're going to start with that. And then I'm going to define the tooling material here at the bottom. So we can come to the drop-down list and use nominal composite in this case. Thickness we had is 20 millimeters. And the last thing we need on the bottom is another heat transfer coefficient. I have some values here, 40 and 30. Typically, they might be upwards of 60, and then good autoclave. I'm just using some middle of the row values here, and often it's lower on the bottom than on the top due to the understructure, and so you have less airflow there. These are fully adjustable, but as I said, that you can only define one number throughout the cycle, so if it does change, that can affect your results. And then the last thing we need to define is a cure cycle. And so I'm going to actually use the MRCC average here. You can see some are predefined, but of course we can edit this as much as you want here. And so this really has a ramp to 132 Celsius, 1.67 BC, and a hold there for 135 minutes. So we're going to say OK here. OK, and I've defined everything that we need to actually run this simulation. And you can see here that this only takes a few seconds to actually run and then populate a plot here that we can see. And so right away, I'm going to turn on the legend so we can see this. It's a little bit big here, but we can see that we've defined several different things. It actually has given us a temperature profile at different thicknesses all the way through. So for clarity, I'm going to turn off the nominal breather because we're not too concerned about what's happening there, and also the tool itself. And now we can see that we actually have the 3 points through the thickness of that laminate. And what we would focus on in particular here is this zone right here, which is this exotherm. And so there's three temperatures plotted here, which are the 3 locations through the thickness. These are actually sort of top, middle, bottom. And I'm going to just look at the middle one because this is most likely to be the highest peak. And if we use a tool like the find maximum value, I can define that here, and that will give us a maximum here. You can go and interrogate this and plot additional properties as needed. And so we can actually do this analysis, and I can actually show you one series here. I'm going to go in and add I need to just select a location, which is right in the middle of that stack up, and I'm going to add degree of cure as well. We'll put that on axis 2, and we can see that here. So now we have the degree of cure as well as the temperature for that location plotted. I'm going to pop back in here into the presentation. And what we can see here is that by filling out a table, something like this, like the peak temperature for each one of these zones, I can actually start filling in these numbers here as we had done there. And then we can actually start to assess where are we going to have the most trouble. Most of you probably know where it's going to be the thickest zone is the most likely to have an exotherm, but we can actually go through and actually quantify that. Additionally, you can put many other requirements on here. So if you wanted to look at minimum viscosity or was the ramp rate achieved, how long was the dwell time, any of these could be requirements put in here, but just for simplicity, we're just looking at one parameter today. So this is the plot that you've seen already. We just generated that in Raven. And so that was the same maximum exotherm there, 135. Now, we move into zone 2. This was a little bit thicker, at 4 millimeters, and we start to see that we're getting a pretty big spike here. We can go in here. This is a little thinner, so we get a lower spike. And then here's the thickest, and of course, this is actually the most troublesome area that we have. So what I've done is actually put in those values here into our little table. And if this was a real requirement or specification, we might have something like a maximum temperature of 150 Celsius. So in this case here, we actually have zone 2 would technically be outside of that. And then zone 4 is the thickest, and it is the most troubling here, being almost 10 degrees above that maximum. So now we have to go and see what we could do about that. So what's really driving this? And so one of the, as I mentioned, we have heat generation that is actually coming from the laminate here. So this is actually the exotherm, and it is pushing heat out. And this is where you actually have the laminate is at a higher temperature than the air temperature. So the heat's going to flow out from this. And what we need is that heat can get out through the breather and out to the top, or into the tool and then through the tool and out. And what's happening here is this composite tool doesn't provide enough of a heat sink for some of that heat to escape. And so this can actually lead to damage, degradation in there, failing the specification. And as I had noted in zone 4, that is our weakest link in this case, so it is the most likely to cause a problem. And so we should focus on optimizing for that zone. So what strategies do we have to employ here? The first one would be slowing the heating rate. And this is often done. Another thing could be to actually incorporate intermediate dwells as well. we're going to look at just slowing the heating rate today. And what this can do is by lowering the reaction rate of the resin, we get less heat generated in the same amount of time, and so this can actually improve our chances of having a successful part. The big thing that we know already is that this is going to increase the production time, and so there's maybe a bit of a trade-off there. And so if I go back into Raven, we can run this same scenario, and we would get now this slightly lower heating rate. And what we see here is that we do, in fact, lower the peak temperature by about 4 degrees Celsius. But it does have, and you have to extrapolate a little here, about a 50-minute extension in the time. And what's more important here is it still doesn't meet the specification. If I had specified 150 degrees Celsius as the max temperature. So we would have to further reduce this ramp rate and increase the time to meet those requirements. Now, another strategy we can look at here is potentially changing the tooling material. And so this is something that can have a significant effect on controlling that exotherm. And this is really a higher heat capacity can absorb more heat, and higher thermal conductivity can conduct that away from the laminate faster as well. And so metal tools typically meet that requirement compared to any composite tool. And so I'm going to actually pop back into Raven here so that we can see what that would look like. And so if I now open up our example here, and we actually had identified it was zone 4 that was the most troublesome, and that was actually at 5 millimeters here. So we're going to change that thickness. We can say, okay, here, let it run briefly. And we'll see that we get this local maximum here, as I'd shown in that presentation. We're a little higher there. I'm just going to extend this window a little bigger so it's a bit easier to see here. So we get this local maximum here, and a high degree of cure. And now we can go in and assess what would changing out the tool do. And so this is as simple as coming into the stack and changing out the tooling material. And in the first case here, I'm actually going to make a change into aluminum. And so we can see what the effect will be here. And so we can see right away, I'm going to change the axes quickly back to where it was approximately there. We see that we do actually have quite a dramatic decrease in the local exotherm. This would actually meet the specification of that 150 Celsius max. We did introduce a little bit more lag potentially here, but really the overall cure cycle time is the same as what we had used before. And so this is what we've seen here, and I actually put these both on the same plot so that we could actually see that this was with the composite tool and then changing into the aluminum tool here. And so there's no additional time. It does meet the specification, but we do know from experience with aluminum tools that this may introduce some dimensional concerns due to the high CTE. And that's one reason why people will use composite tools, is to have a much lower matched CTE. So we could go to another tooling material, something like Invar 36. That's got a very low CTE, and that's one reason why it's used in industry. Again, this does meet the specification. You actually see the maximum is very, very close to the end. It's essentially, it doesn't really have an exotherm, and so this tool is very good. But it does introduce some lag, and that lag might affect our final degree of cure enough that we might have to actually extend the cycle. And so what would we do about that is what we can do in Raven is actually investigate the degree of cure. And that's very much what I had done here. If I come back, is including degree of cure on this plot here. And so we can actually see what that effect is quite quickly and compare different cycles. If we jump back in here, in this case here, we actually have a reduction in final degree of cure of about 1.1%. That may be due to the length of time here, but it's also probably due to this spike in temperature is actually effectively curing at a higher temperature as part of that laminate. So if we can live with this slight reduction, then this might be a good strategy going forward. using an InVar tool. And of course, there are different costs associated with the tools, but it's something to consider. And so, in summary, what we've seen today is that thermoset resins can have these non-conformance, really due to their inherent cure and exotherm. Thicker sections are a little more susceptible, and that's something I think most people intuitively know. At some point, you will get to a thickness that you are not able to actually use a tooling change or solely a tooling change to actually address that problem. And that's where you need to use multiple strategies, including changing the cure rate and or changing the tooling out. So slower heating rates definitely help. Introducing intermediate holds can also be used, but in each of these cases, we have additional processing times, and so there's a cost associated with that. The tooling materials can really influence the analysis and that exotherm, but again, we have some other different things introduced, and that's that thermal lag and potential dimensional concerns, as well as the potential cost of those tools as well. So these are all things that you need to balance when you're designing a cycle like this. And if we look at the tool that we're using here today, which is Raven, to do this analysis, I think you can see that the 1D drill through is a really great way to quickly assess these different changes and assess what the trade-offs would be between cure cycle changes, tooling material changes, and other assessments that you can make. And this is a really good way to try them and then gauge their effectiveness and actually make an informed decision about a choice. But it's not just limited to temperature, and so that was one of the reasons I had shown degree of cure, but you can also look at many other properties that is anything that has been characterized for your material, and that can really go into a much deeper understanding of what the effect would be of one of these changes. So glass transition temperature, viscosity profiles, these are all things that can be done within Raven quite easily. And so that's the end of the main presentation here. And so if there are any questions, please type them into the host, which is Nick Tuccini here. If you do have some other questions that come up, if you afterwards, feel free at any time to email us, info@convergent.ca. In addition, we are recording the webinars, so we'll be able to make those available to people that are interested. And I want to advertise our next webinar is actually going to be on November 21st. It's a little bit early. I think it's around the U.S. holidays around Thanksgiving. And so we're going to be looking at cure cycle optimization next time around with Raven. So I'll open it up if there are any questions.
So the first question was if we send out the PowerPoints or send out the recordings of the presentation.
And absolutely, yes, we're recording today, so we'll send that out and we can definitely provide the slides as well.
Another question that came in is whether or not you can change the heat transfer coefficients in the simulations.
Sure, so I'm going to go back into Raven here and we can go full screen. And so that's actually one of the other strategies that people might think of looking at here is given a tool that we have, and I'm actually going to swap back to our composite tool here. That might be one strategy is what if I put my part in an area in the autoclave with much better heat transfer, so right in the airflow. So we'll go up to a number here, 60, for example. And you actually get a little tool tip here as well that gives you some typical values. Really, it's anywhere from 5 to 100 are possible or likely in an autoclave, but typical values is 10 to 60, 60 being sort of on the reasonable, good airflow side. So we can actually run this here quickly. We'll see that we have quite a big spike here. I'm going to have to change the axis here. 180. Here. So we can see this. Now, one of the things that you might say, if I have this high heat transfer coefficient, what is the effect going to be by changing it in here? And so we can see in this case, I'm going to go back down to my 40 and 30. And, you know, will this help with this exotherm? We're at 161 here. You can see actually that this will have a relatively small effect, but it does affect things. And it is something that you can definitely look at trying to do, but it's definitely not going to have nearly the same effect in this case as the tooling change.
Another question, I guess, related to our other software is whether we can model breather in Compro and how to model it. So I guess it's not necessarily related to this webinar, but you can include breather in your FE simulations. Again, since we have the nominal breather here in our material database, you can, but it's only characterized for the thermal properties, so you can't run it for a stress deformation analysis. So if you're just looking for a thermochemical simulation, yes, it's typically just modeled as a, you know, it's a thin layer, so it's just modeled one element through the thickness. And yeah, it's no different than modeling the rest of your structure.
Yeah, and I have one other thought around that is that what it does is it effectively puts a little barrier, a little bit of insulation on the top, and so it will just slow down that heat transfer. Now, depending on how you've calibrated your heat transfer coefficient, you can essentially lump that into your effective heat transfer coefficient. And that's something that's often done in practice, is that we would simply leave out this layer, but then we would adjust the heat transfer coefficient above to be equivalent. So it would then, in that case, take both the you know, the actual convective heat transfer coming onto that top surface, then the conduction through the bagging material, then the conduction through the breather material to the top surface. And so you can lump all of that into an effective heat transfer coefficient, which is really just a way to translate the applied air temperature in this case to the top of the laminate. And this is something that I think in the future we're going to have another dedicated webinar on, is how to back calculate heat transfer coefficients from thermal data, because that's the easiest way to come up with realistic ones for your particular case. And if I run the simulation here, we can see that it'll affect things a little bit, quite a bit more actually, because what we're doing is reducing that insulative properties on the top of the laminate there.
Another question is if you don't have a process in an autoclave or oven, can you use other types of heat transfer mechanisms?
So, yeah, so if we're using an oven, most likely you can use the same idea of applying the air temperature and a heat transfer coefficient. There, it would just be much lower, maybe around 20, 30. That might be more like a good industrial oven, and if it can be lower than that. But you can also apply a different boundary condition here, which would be a set temperature. And in case of a set temperature, that actually applies the boundary condition directly on the top here. And that can be used either to use, I'm going to show you where we define that cycle. I had defined it here as a straight ramp and hold. However, you can actually do this cycle from data here, which is grayed out. I haven't loaded any data in. But this also might be if you had for example, a heated tool or a platen, that would effectively be like setting the temperature on the top of the part here. And so in that case here, we actually see, so if I run this case, we'll see that what happens is the part itself will follow very, very closely, and we eliminate that lag, because that lag is associated with that resistance from the heat transfer. And see here, we actually follow very, very closely. And of course, we're looking at the central temperature in this case here. We see a very small exotherm. So I think that's all of the questions we have for today. We will be sending out, if anybody's interested in the recording, we can send that out. And as well, if any questions come up later that you didn't think of right now, feel free to email info@convergent.ca and we'll be happy to follow up with you as well. And if you have any of your colleagues that you'd like to pass this along to, we'd be happy to provide them with the recording as well.
All right. Okay, if there's no more questions, we'll end the webinar now then. Thanks for joining in, and again, if there's any more questions, please let us know.